Hello everyone, welcome to my channel Coding Together. My name is Vikas Oja. Today we will see another Leetcode problem, that is redundant connection. So it's a medium level question. So let's read the problem statement. So in this problem, as we know, the tree is an undirected graph that is connected and has no cycles. So we are given with a graph that has started as a tree with n nodes labeled from 1 to n, with one additional edge added. The added edge has two different vertices chosen from 1 to n and was not an edge that already existed. So the graph is represented as an array edges of length n, where edges I equal to ai comma bi, indicates that there is an edge between nodes ai and bi in the graph. Return an edge that can be removed so that the resultant graph is a tree of n nodes, right? So let's see an example to better understand the question. So if you can see, this is a graph with a cycle. So to convert it into a tree, we have to remove the redundant connection or the edge that will that is causing the cycle nature of this graph. So if we remove the edge 2, 3, then the resultant graph will be a tree with no cycles. Similarly, this undirected graph has a cycle like 1 to 2, 3, 4 and again 4 to 1. So if we remove this edge, then the resultant graph will be a tree with no cycles. So let's see the idea or the intuition behind solving this problem. So suppose we are given a graph with the node 1, 2 and 3, and there is already an edge between 1 and 2 and 1 and 3. And if we are trying to add an edge between 2 and 3, then it will be a cycle. But how would we know that it's a cycle? Because there is already a path. There is already a path between 2 and 3. There is already a path between 2 and 3 if you see this, and means they are already connected, or 2 and 3 belong to the same connected component, right? So if we add edge between 2 and 3, it will be a cycle. So this information can be maintained in a data structure called disjoint set data structure, which will maintain the information of the connected components. And with the help of the two operations, union and find, we will be able to know whether adding an edge between the two nodes will form a cycle or not. So I have already created a video on disjoint set where I have already explained what is disjoint set and what are the two operations, union and find. And in the part 2, we also talked about the optimization of the same with path compression and union by rank. So if you have not watched that video, I would recommend you to go to that video first and watch that video, and then you can continue with this video. So let's see an example to better understand the concept we discussed and how disjoint set will maintain the information of the connected components and help finding the cycle. So now we have this list of edges, and at the start for each node, right, we have maintained the parent array. So at the start for each node, the parent will be the node itself, right, because we can consider all the nodes as the different components. We'll iterate from the first edge, and the first edge we'll iterate from the first edge and we'll do the union of 1 comma 2, right? So as we know, the union means first performing the find operation on 1 and find operation of 2, and then we'll check whether the ultimate parent of 1 and 2 are same or different. If they are same, then we'll return false, right? And if they are different, we'll return true, and we'll combine or will union them. So to perform the find operation on 1, we'll scan the parent array that is starting from the node 1. So for node 1, the parent is 1 itself, so find of 1 is 1, and for find of 2 is 2, right? As they are different, so we will combine 1 and 2 into the one component, and we'll change the parent pointer of 2 pointing to 1, right? So now the parent of 2 will be 1. Now we will again perform the union on 2, 3. So union 2, 3 is again first finding doing the operation find on 2 and find on 3. So find on 2 will be scanning the parent array starting with node 2. So the parent of 2 is 1, and for 1 the parent is 1. So the ultimate parent of 2 is 1. As we can see, the ultimate parent of 2 is 1. So find of 2 will be 1 and find of 3 is 3. So as they are different, the ultimate parent of 2 and 3 are 1 and 3 that are different. So we will return true, right? That we have to make a union of 1 and 3 because they are not they are not connected already. So we will change the parent of 3 to 1, and we'll also change the parent array for the 3. Now the parent of 3 will be 1. Now the next edge is 3, 4. So we will do union 3, 4. So first we will perform the find operation on 3 and find operation on 4. So find operation of 3 will return will scan the parent array starting from node 3. So for node 3 the root the parent is 1, and for 1 the parent is 1 itself. So we'll stop here and we'll say that the ultimate parent of 3 is 1 and the ultimate parent of 4 is 4. So as they are different, the ultimate parents are different, so we will return true and we will union them as they do not belong to the same component. So we have to union them. So we'll change the parent of 4 to 1, and we'll also change the parent of 4 to 1. Now we have another edge that is 1, 4. So we'll do union 1, 4, and we'll do the find operation on 1, 4. So find of 1 is 1 and find of 4 is also 1. So they have the same parent. Now we'll return false. So we'll return false from here, right? We don't want to add the edge because adding this edge will create a cycle, as from the connected components maintained by the disjoint union set we know that there is already a connection between 4 and 1. So let's see the code part for it. So we have reused this DSU class that we discussed in the disjoint set video lectures, part 1 and part 2. The only difference is while doing union, if the root of x and the root of y is same, then we're returning false, otherwise we are returning true, right? And what we are doing in the main function, we have taken a maximum edge value that is 1000, because in the constraint it's given that the n is greater than equal to 3 and less than equal to 1000, and we have initialized our DSU with that max edge val plus 1, and for each edge we are performing the union and over the node 0 and node 1, and if the node 0 and node 1 have the same root, then we are returning false, right? And this we are returning false, and this condition becomes true, and when the if condition becomes true, we are returning the edge to be removed to make the graph acyclic or to make the graph a tree. Otherwise we are returning an empty integer array. So let's talk about the time and space complexity for this algorithm. So as we know, for the disjoint set data structure union operation, the time complexity is constant time, and we are performing n union operations, so the time complexity will be big O of n, where n is the number of edges or the number of nodes, and the space complexity as the graph embedded into the disjoint set has at most n nodes, then the space complexity will be also big O of n, where n is the number of edges or the number of vertices. So I hope you like this video, and if you like this video, please share and subscribe. Thanks for watching. Bye.